Mid and high efficiency gas-fired forced air heating systems. In this presentation, we're going to be looking at the types of mid and high efficiency systems that exist in the heating industry, the basic construction of them, components, the sequence of operation, and finally, flame ignition. Up to this point, we've been focusing on a basic gas-fired heating appliance. And again, we want to ensure that you understand that the concepts we learn in reference to heating systems is not solely focused only on a furnace. This type of heating system is ramped up into much larger applications in the commercial and industrial sectors, but the sequence of operation and the components that we look at will remain consistent. What we're going to focus on in this presentation is the combustion gas that comes out of the furnace at this point. How hot is it? If it's really hot, that would then lead us to believe that the heating system itself is quite inefficient because this gets vented outside and that heat energy is lost. How much heat energy is lost and what its efficiency rating is determined by EnerGuide, and it's given as an AFUE rating, annual fuel utilization efficiency, and it's given as a percent. Low efficiency or standard or basic conventional older furnaces are only about 55 to 80% efficient. And that's because the heat exchanger is very basic. It simply burns the combustible fuel, the heated gases move straight up through the heat exchanger, and immediately they are vented out. As the most learned individual will know, it's really freaking hot, and you can burn your hand if you were to touch that metal flue vent in the wrong place. Now, what this means is that a ton of heat energy is lost to the system. We have furnace room air that comes in with the burner gas and it burns it together and off it goes. So 55 to 80% efficient is about what we would expect from a furnace from the 30s up to the uh, early 80s. This is what the heat exchanger would look like. And as you can see, there's not much obstacle for the combustion gases to flow up through this wavy item and then up and out. We're depending on convection, a heated gas, to move its way vertically up and out of the furnace and out of the house. And here's an example of one of those older standard furnaces where we see that big metal vent coming up and out, and it then connects into the chimney section of this particular home. The air in the furnace room would be used to burn the fuel inside the burn chamber or the burner assembly, and the combustion gases would then come out through the flue. By contrast, a mid-efficiency furnace is around 80 to 90% efficient, and this was the standard from about the mid-90s until the aughts or 2000s. And what we have here is an exhausted combustion gas out that's only about medium hot. And the reason for that is the heat exchanger is much longer and winding. And in doing that, we have much more surface area for the heat to be removed from the combustion gas and transferred to the warm air in the house. So now that it takes a long path to get out, we need some form of a secondary fan to like suck these through because they get so cool that they won't actually move on their own. Remember, the only reason that the combustion gases rise in the standard efficiency furnace is because they're so hot. In a situation like this, we would expect a heat exchanger to have more surface area, look a little bit different, a little bit more modern, but you would still expect the metal flue vent to come up out the top in the form of this corrugated or galvanized metal and poking up through the top of the house because it's still quite hot. So these are double-walled metal pipes, also known as B-vents, and these are common to be seen with low and mid-efficiency flue venting. Finally, high-efficiency furnace, also known as a condensing furnace, is 90 to an astounding 98% efficient. It uses two separate pipes to bring in air to burn for the combustible fuel, and it also has a pipe to remove the combustion gas at the end. They're both plastic, and the reason for that is they are barely warm. Now notice what's happened now. We have a large surface area heat exchanger, but now it goes through something called a secondary heat exchanger, and it's forcing the combustion gases down as opposed to up. If it forces them down, that means they're going to stay in the pipe longer and more of the heat energy will be removed from them. The secondary heat exchanger is simply another shape which takes even more heat away from those combustion gases so that by the time it finally leaves the house, it's barely even warm. Again, we're going to need some form of a motor to suck these fumes through because they will be so cool by the end that they will not move naturally on their own. High efficiency furnace will cool the combustion gases so much that the moisture in those combustion gases will condense into a liquid, hence the name condensing furnace. The liquid is collected at the base of the heat exchanger and then piped to a floor drain. Sometimes an electrician will have to install a small sump pump if the nearest drain is further or up above elevation where the actual furnace drain is located. This is an example of some high efficiency heat exchangers. You can clearly see a primary, which is the larger tube, and then the secondary heat exchanger, which resembles more of a radiator. This is what the venting would look like, where we have two plastic pipes. One plastic pipe brings air from outside to the burn chamber to be burned with the gas, and the other pipe is the exhaust pipe for those combustion gases. There's no metal venting. And so the outside of the house, you may have something like this. So here are some of the different heat exchangers that we've looked at. Now, a mid and high efficiency furnace have a slightly more complicated order of operation. It's not crazy, and what we're going to find is it's actually quite basic for us to memorize the process of what to expect when a call for heat is found. A mid or a high efficiency furnace is going to have all of the main components of a standard furnace, but in addition, a combustion air-proof switch, a combustion air blower, still have a main gas valve, still have a fan blower assembly, but because it's more modern, it's going to have a ECB or an electronic control board. There are many different names for this particular fan that is located in the combustion gas circuit. It moves the cooling flue gases through the heat exchanger. And depending on the manufacturer, they could call it a combustion air blower, flue gas vent blower, system purge, all these different types. Essentially, the purpose is to move the combustion gases through the heat exchanger. This is found on much larger heating systems that are forced air, as well as large boiler systems in the industrial sector. At times, you may see slight differences when it comes to the arrangement and position of these different types of fans. But again, their intent, the main purpose of them is to move the flue gas or combustion air up and out of the building. Because of this, there needs to be a little bit of sequence when it comes to when this will turn on. The combustion air blower will start before the main burner is ignited, and that's to establish a flow of air through the heat exchanger in the correct direction, which is out of the house. It will obviously continue to turn and to pull that airflow through the heat exchanger during a burner heating cycle, which is to say, when the burner is ignited and burning, this fan still turns. And finally, after the burner extinguishes, there will still be some combustion gases left in the heat exchanger. And so because of that, this fan will continue to run for a specific period of time after the burner is extinguished. Now keep in mind, the furnace needs a method of confirming that the combustion fan is running. If it were not, combustion gases or carbon monoxide could fill the furnace room. And obviously, when people die, that's considered a bad thing. So in order to prove that the combustion air motor fan blower is actually operating, we use what's called a pressure switch. Now, that it operates on suction is not really important, but what is that it confirms airflow through the heat exchanger. It's a means of proving mechanically that the fan is operating, but not just that it's turning, that it's actually doing what it's intended to do. So a pressure switch is located in the furnace with a small plastic tube that senses the air pressure difference. If we look in a standard furnace, we'll see that the pressure switch and the combustion air blower are connected together with this small plastic tube. Now, the purpose of this particular switch is to confirm the air movement. And after it has determined that there is air movement for a predetermined amount of time, the control board will energize the gas valve to its open position. The furnace must also be able to confirm that flames remain inside the burner area. And in order to confirm this, we want to utilize electrical heat sensitive devices that will notice this. This is called a flame rollout condition. And if it were to occur where the flame comes out of the burner assembly, we want the furnace to automatically turn off. In order to do that, we use bimetallic operated snap disc types of heating switches, where they are rated for a specific temperature and they will operate at that temperature and either open or close a set of contacts. They come in many different shapes and sizes. Usually it's a normally closed, which then snaps open when the rate of heat level is applied. Usually these will automatically reset when the temperature decreases below its rated value. And sometimes there's a manual reset button, which forces an individual to go and inspect and make sure that nothing has been damaged prior to resetting the furnace system. If a flame rollout sensor is triggered, it will cause the control board to de-energize the gas valve and cause it to go back to its closed position automatically. Now, high efficiency furnace gas valves have no pilot valve, no pilot burner, and no thermocouple or power unit. And the reason for that is because a pilot valve and a pilot burner is highly inefficient. If we have constantly gas being burned, that means that it's being used for nothing that it's intended for, as in it's not heating the building. And that is not seen as a desirable outcome. In a conventional furnace, we're always burning this gas, and this also leads to its lower efficiency rating. In a mid and a high efficiency furnace, we have lots of controls, and those controls will monitor when there is a flame and ignite the flame, but not with a standing pilot. There are two main ways a main burner ignition system will ignite the gas or the oil in a mid or high efficiency heating appliance. The first one is called direct spark ignition, and the other is hot surface ignition. Sometimes these are abbreviated as DSI and HSI. Direct spark ignition is, as it sounds, a spark. Looks like a spark plug, and essentially it comes with a high voltage source that initiates a spark across a gap, which ignites the gas. In this way, we don't constantly have a value of gas that's being burned constantly for no reason. Here's a order of operation that looks at direct spark ignition inside the furnace, but remember, we still need to have a form of flame proving. How does the system prove that a flame is present? Well, that is done with a secondary object called a flame rod. Now, a flame rod is simply something that will be in contact with the flame. Now let's see how the entire system will operate. When there is a call for heat, we already know that the combustion air blower will run for a time, and when the pressure switch closes, it will then allow for the furnace control board to ignite the main gas. The main gas burner will open, allow gas to flow, and then it will ignite it at the same time. As soon as it's ignited, there needs to be a means of proving that a flame is present. And the way that most modern heating appliances will accomplish this is through use of a flame rod. Flame proving takes a small value of millivolt AC, passes it through the flame, and measures the return signal. It is slightly reduced and it is rectified to DC after passing through the flame combustible particulate. If the furnace did not see this return signal, it would rightly determine that no flame was present, and in response to that, should turn off the gas burner. Here we can see an example of these three objects: the main gas burner on a demonstration unit, the spark plug, which creates the spark to ignite the gas, and here the flame rod, which is in contact with the flame and is constantly evaluating that a flame is present. If the control board does not receive a confirmation of flame signal or proving that the flame is present, the gas valve will again de-energize or go back to its mechanically closed position. Hot surface ignition works very similar, but other than instead of a spark, we have a hot surface or a red hot element which ignites the gas. Hot surface ignition works very similar in that there is a hot surface and a flame rod. The process that we look at is very similar. The hot surface gets exceedingly hot, red hot, so that when the gas is allowed to come out of the main gas burner, it immediately ignites off of this surface. At that point, it's de-energized, and the control board then evaluates to see if there is a signal coming back from our flame rod in a very small volt DC signal. Again, if a control board does not receive a confirmation of flame signal from the flame rod, the gas valve will be de-energized. So all of these different items come back to the central control board, and a basic schematic can no longer really be used to trace everything that's happening within the system. Let's take a look at a standard wiring / schematic diagram that may be found with a modern heating system. Holy smokes, not really a schematic and not really a wiring diagram. It's sort of both blended together. And this is what you could expect for most complicated systems where there is some form of a control board and different types of items or pilot devices that interact with either heat or pressure or leverage. What we can identify just with our basic knowledge is different symbols indicating different objects. These are high limit switches, and there appears to be 3 of them in this furnace. There is also rollout switches. There appears to be 2. All of these are normally closed, which would lead me to believe that in order for the operation to take place, they must remain in the normally closed position. Up here, we have the flame sensor. It connects into the control board. And finally, we have the pressure switch, which we can see from the semicircle shape, and it is normally open. Under normal conditions, when the furnace is not operating, it should be open, and when it's operating, when there's a difference of air pressure, it should then close. We see down here that there's a connection for the main gas valve, and there's also a spark electrode. Down here is where the 120 volts are, and we see that there are 2 separate motors. The motor here is the smaller of the 2, and this one would be the combustion air blower. This one over here is actually a multi-speed motor, depending on if we're doing heating or cooling, and this would blow the air throughout the building. All the way on this side, we see that there is a limit switch, and this is then controlling when 120 volts is even applied to the furnace based on the cover door being in place on the actual appliance itself. So although we can't follow everything inside from point A to point B like a typical schematic, we can utilize the information shown on it to try to determine if a device or an item is broken or damaged. So what is the process of operation for a standard mid or high efficiency heating appliance? Well, order is the same for both mid and high efficiency, and we're going to look at each one of the steps here. First, as in all heating systems, a thermostat is set higher than the actual temperature of the room it resides in. The contact inside the thermostat closes. Now, in a mid and high efficiency system, what that does is send a signal to the control board. And the control board then takes that information and turns on the combustion air blower. This runs for a predetermined amount of time based on what the manufacturer feels is acceptable in the 20 to 30-second range. At this point, an airproof switch should close. And once it does, it should close the electrical contacts and send a signal back to the electrical control board. At this point, the system now knows that the combustion air blower motor is turned on and we have airflow through the heat exchanger. At this point, it will turn on the gas valve and the ignition source at the same time, so that as soon as gas is released into the burn chamber, it is ignited. At this point, we need another confirmation. And the confirmation is that the flame is proven to exist. The flame proof sends a signal back to the ECB or the control board. And again, this allows for the flame to continue going. The gas valve remains open and the flame continues. At this point, finally, is when we get the control board to turn on the main blower, which now starts to blow hot air throughout the entire building. We've got 1, 2, 3, 4, 5, 6 steps. And these are standard steps that we would expect in almost any modern heating system. There is a combustion air blower. There is an air-proof switch to prove that the combustion air is actually moving. There is then a flame-proving section that determines that, yes, indeed, there is a flame present. And then finally, at the very end, the main blower starts. Now, understanding this sequence of operation is important when we go to troubleshoot a mid or a high efficiency heating system. And as electricians, we're often called to different types of installations that could blend between two different trades, such as an HVAC technician. The majority of the HVAC controls are electrical in nature, and we do have the skill set in order to accomplish and determine the cause of the issue. HVAC has a lot of time-sensitive requirements when it comes to trouble calls, and getting into that sector of the industry can be highly profitable. In order to accomplish this, though, we really need to know that order of operation. So let's take a look at a very basic example. Customer calls you and says their furnace does not turn on. You arrive and you take a look at the thermostat. First thing, remove the wires and measure the ohms between R and W. If we set the temperature above the room temperature, what we should see is that the continuity, when the temperature is set high, it should be, well, present, as in there should be a very low ohmic value between terminals R and W, and that's because the temperature switch should close. So if we measure this, then that means that my thermostat is good. We move down the chain. When I set it high, the combustion air blower turns on. I can hear it down in the furnace. It comes on and I'm waiting to see what happens with the sequence of operation and checking it off in my mind. It comes on, it remains on for 20 seconds, but then it just turns off. The main burner does not ignite, the main blower fan does not turn on. So what does this tell me? Well, the sequence of operation is what I rely on. The sequence of operation tells me that before the main burner is permitted to ignite, the air pressure switch must close, proving that the fan is running. So we need to now inspect the air-proof switch. We can remove the electrical connections and check the continuity of the contacts. Well, let's go back to our diagram. It looks like it's a normally open, and that tells me that when there is no pressure, I should have a very high ohmic value across the electrical terminals. We're looking at this symbol here. When the pressure changes, then the contact should close, and I should see a change in continuity. So what we're going to do is set our multimeter to continuity setting, and with an expectation in the back of my mind for what should occur. What should happen? Well, when we put our continuity set meter on the contact, when nothing is being applied in the form of pressure, we should have no sound, as in OL ohms should be displayed. When I blow or suck into the tube, kind of depends what type it is, we should get this really annoying ringing sound from my multimeter, and that would tell me that there's continuity. The ohmic value should be extremely low. So this is what should happen. If I don't know what should happen, then it would be difficult for me to interpret results when I go and do it on the actual piece of equipment. So here we have our ohm meter set to continuity, or a multimeter set to continuity. What actually happens, so there's no sound. I'm not doing anything to the pressure inlet or outlet, and it looks like that would be a normal expectation. Now I blow or suck into the tube, but there's still no sound, and it's still registering as OL ohms. So what this tells me is that the air-proof switch is faulty. It's reached the end of its life. We don't need to go any further other than to say it needs replacement. Now, this is a common series of steps that an HVAC technician would take into account. Knowing the sequence of operation is important when determining what the fault is in the system. Another way that we can troubleshoot types of heating systems is through LED flashing. And these are in a series of codes, almost like Morse code, number of short blinks and number of long blinks. And usually the status code LED is on the control board itself. And at times there is a small window that you can actually see this light and a very small label that indicates what different flashing sequences mean. And so this can help to expedite the troubleshooting process. Don't shy away from HVAC and HVAC industry types of jobs. There is always a need for HVAC technicians and individuals who can appropriately understand how the system operates.